Okay, in this lecture, we'll go over generative models for classification. If you recall, logistic regression involves directly modeling the conditional probability of the response given the features, probability of y given x, and we use the logistic function. So we model the conditional distribution of the response given the predictors. Now, an alternative way of looking at this would be an indirect way. In this approach, we first start by modeling the distribution of the predictors. So, distribution of the predictors separately in each of the response classes, meaning for each value of y. And we refer to it as fk of x. Little k here indicates the response class. So if k is 1, this distribution is going to be different from when k is 2. So again, we model the distribution of the predictors x separately in each of the response classes, essentially meaning for each value of y. Then we use Bayes' theorem to flip around these probabilities into what we call posterior, what we call just this conditional probability of the response given the features. Okay. Now, if we assume that the distribution of the predictors for each y is Gaussian, it turns out that if you do the math, we get something similar to logistic regression. That's something you saw in the previous lectures. But in general, what we are doing is here presented. This is Bayes. This is, we want to find the distribution, the conditional distribution of the response given the predictors. This can be written as the probability of y being equal to k and x being equal to x, little x, divided by the probability of x. We call this the marginal probability or sometimes density of x. Why marginal? Because it does not depend on what the response category is. So what is the distribution of x regardless of the response category? That's px. Now, probability of y being equal to k and x being equal to little x can be written as the probability of x being equal to little x conditional on y being equal to little k times the probability of y being equal to little k. And this is what we have already defined here. Now, what about the marginal density of x? probability, the marginal probability of x, this has to be L. L from 1 to capital K, uppercase K, is probability of x being equal to small x and y being equal to small l. Then we break that into a conditional probability times the probability of y, and probability of y being equal to L, we use pi of L, and the conditional probability of x given y is equal to L is FLX. This is Fk of x. This is Pk, pi k. So to summarize, this is a generative modeling approach where we say, okay, if the features are this and this and that, the probability that the label is little k is this. And this is how it's computed. So this is a general approach, and depending on how we set these densities, we will end up with different models. And typically we take the log of this probability to get what we call a discriminant function. So this discriminant function will assign a score to every class, every category, and the class that has the largest score is typically the assigned class. So we assign new observations to the class for which the discriminant function is largest. So if we assume that the distribution of the features within each category is Gaussian, where the mean is only different but the covariance is the same, we will end up with something that is known as the discriminant analysis. So the features are distributed as Gaussian distributions with the same covariance, different means. Gives us linear discriminant analysis. Here we are looking at the bivariate Gaussian density, you see that it is it doesn't have a specific orientation, so the features are uncorrelated. But we can also have correlation, and here the features are correlated, and this has an orientation. But for linear discriminant analysis, we assume that this is this is a Gaussian density, but for linear discriminant LDA assumes that the observations in the Kate class are drawn from a multivariate Gaussian distribution, normal with mean mu. So it's a class-specific mean vector, and sigma is a covariance matrix that is common to all K classes. So if we plug this into our formula, this, and you do the math, which I will skip, it is tedious, but it is straightforward. I skip that. I suggest you do it at least once for yourself, so you get this discriminant function. This is a Bayes classifier. So for any new feature, we take the transpose of it, multiply it by the inverse of the covariance, then we multiply it by the class-specific mean vector, and then minus 1/2 this term, plus the log prior probability. So any class that has a large prior probability is also has this initial advantage, because the log of that probability is going to be larger. Now if you have three classes, then you have these three Gaussian distributions. You see the orientations of the distributions is the same, so this is a sign that the covariances are the same. Just the means are different, and these become the decision boundaries. So for any combination of x1 and x2 that is in this area, the discriminant function for blue is going to be the largest. Now, as we saw before, these parameters, we don't know them. We have to estimate them from the data. And since estimates are noisy, this is the boundaries of the optimal Bayes classifier. These are Bayes decision boundaries. When we have perfect information about the class-specific means. Now, when we don't have them and we estimate it from the data, as we can see here, or covariance estimates and our means are slightly perturbed. So the decision boundaries will be slightly different. So the solid ones refer to the LDA, which estimates things from the data, and the rest are from the and the dashed ones are the Bayes decision boundaries. And I mean, I think we went over this. So if you haven't read this section, read it. It's very important. And make sure you understand every sentence. Next is quadratic discriminant analysis. In quadratic discriminant analysis, we still assume that the features have a Gaussian distribution, but we allow some extra flexibility by letting the covariance to be different for each class. Therefore, we do not have sigma, we have sigma k. If you do the math, it will lead you to the following discriminant function. And it's called quadratic discriminant analysis, not function analysis. Why? Because the dependence of the value of this function on x is quadratic. You have this x here, you have this x here. So you have x minus mu k transpose, and then you have x minus mu k. Whereas for the linear discriminant analysis, the function is linear in x. So you have one x here, but then the rest here is just sigma inverse mu k. So this is linear. This doesn't have anything to do with x. This doesn't have anything to do with x. So the dependence of this function on x is linear. That's why this is called linear discriminant analysis. And that's why the decision boundaries are also linear. So the number of parameters in quadratic discriminant analysis is larger. Why? Because a covariance matrix, a p by p covariance matrix, is going to be symmetric. Therefore, it has p times p plus 1 over 2 parameters for each of the covariance matrices. And since we have k of them, it's k times p plus 1. So if you have 50 predictors, we need to estimate 1275 parameters only for the covariance. But for LDA, well, we have the means. Each mean has p variables, so it's kp of them. But that's the same for quadratic discriminant analysis. But for LDA, you only need to estimate p times p plus 1 over 2 parameters because the covariances are the same for all the classes. So QDA gives us an extra flexibility. The cost is that we need to estimate more parameters. So roughly speaking, LDA tends to be a better bet than QDA if there are relatively few training observations. Why? Because when we have relatively few training observations, that means that to begin with, or the amount of information available in the data, there's a limit to it, obviously, and there is not much here. And when there is not much, if we fit a model that is complex, that is more complex than the information available, then that model will tend to adapt to the variabilities in the data, which is different from the pattern, from the structure that we want to capture. So we want to reduce the variance, therefore we estimate it using a simpler model. But if we have a very large training set, then yes, that means that we probably have enough information in the data so we can accommodate a more complex model. So I pause here a little bit so you have time to read this. So on the left, purple dashed is the Bayes classifier. If you look at this cloud of yellow and this cloud of blue, you see that the orientation of the distribution is more or less the same. The spread is the same. So this is a data. It's a synthetic data, but the generating process is such that the covariances for each class are different. Sorry, that the covariances for each class, for the both classes, are the same. Only the means are different. And if we would use the true covariance and the true means and the true unknown prior probabilities, we get this decision boundary, which is the Bayes. If we were to estimate them from the data using LDA, we get the black dotted line. And if we would use quadratic discriminant analysis, then we would get this decision boundary. Is it reasonable to use quadratic discriminant analysis? Well, in this case, because we know that the data originated from two Gaussian distributions with the same covariance, using a quadratic discriminant, using quadratic QDA here is moving into the territory of overfitting, because QDA provides a flexibility which in this, for this data, is unnecessary. Now on the right hand side, if you look at the cloud of the yellow, the orientation is this way. The blue cloud, the orientation is this way. The orientations clearly are not pointing in the same direction. So it is reasonable to believe, I mean, here we know it again because this is synthetic data, but you can see that the data is generated from a process which assumes that the covariance matrices for the two classes are not the same. The means are different, the covariances are different, and therefore the Bayes decision boundary, which would use the true unknown covariance matrices and the means and the prior probabilities, would yield the purple dashed line. So if an oracle would give us sigma 1 and sigma 2 and mu 1 and mu 2 and pi 1 and pi 2, then we could come up with this decision boundary, the purple dash. That's the best thing we could do. But since we don't have an oracle and we estimate everything from the data, QDA, which is green solid, is going to be slightly different than the Bayes decision boundary. And if the amount of data that we had here and here would increase like tenfold or 100-fold, these two curves would get closer and closer to each other. So the more data you have, then these two will get closer and closer. I mean, assuming that the data generating process remains the same. LDA, on the other hand, because it assumes that the covariances are the same, ends up with a linear decision boundary, and that's what it will tell us. So that's the story of QDA. Next, we go to NaiveBayes. Okay. So again, we're going to use the Bayes rule, the Bayes theorem, the same way everything we did. The only difference is that NaiveBayes makes an assumption here. You see the major difference that we get here between QDA and LDA was due to the assumptions we made about the class-specific distributions of the features. If you have P features, these P features are almost always dependent. And the structure of this dependency is complicated to capture. To begin with, we don't know it and we have to learn it. And because it's complex, we always try to make simplifying assumption. LDA's simplifying assumption was that this class-specific distribution is Gaussian, the covariances are the same, the means are different. QDA said, great, we want to go one step further, so we still say they are Gaussian, but the covariances can also be different. Now NaiveBayes goes in another direction and says, I don't want to necessarily make it this assumption about whether it's Gaussian or not. The major assumption I'm going to make is that the joint distribution factors into the multiplication of the marginal distribution. And essentially what it means is that the features are independent of each other, which is not true, but in practice we learned that this simplifying assumption allows us to fit data that comes from sources which sometimes it is not reasonable to assume that they are Gaussian, and even the simplifying assumption allows us to do a lot of things, and the naive-Bayes classifier in many applications performs well. So the major assumption here is this, formally. So instead of assuming that these functions, these ones, this ones, f1x, the distribution for class 1, class 2, class 3, that they belong to a particular family of distributions, for example, multivariate normal, we just make the assumption that within the kth class, the p predictors are independent. So mathematically, this assumption means that for k going from 1 to uppercase k, we can write the joint density as the multiplication of the densities. And why is this assumption so powerful? Essentially, estimating a p-dimensional density function is challenging because we must consider not only the marginal distribution of each predictor. This is a marginal distribution of first predictor. This is the marginal distribution of the second predictor. This is the marginal distribution of the pth predictor. This is the joint distribution of all of them. So why is it difficult? Why is this assumption powerful to make this assumption? Which is not true, obviously, but we make that assumption. Because estimating a p-dimensional density function is challenging because we must consider not only the marginal distribution of each predictor, but also the joint distribution of the predictors. We must consider the association between the different predictors. In the case of a multivariate normal distribution, the association between the different predictors is summarized by the off-diagonal elements of the covariance matrix. So for a Gaussian distribution, all you need to tell us is what is the correlation between, what is the covariance between any two variables. When we know that, then we know the whole joint distribution. That is not true for other distributions. So the Gaussian in that sense is a simpler one. In general, as I said, this association can be very hard to characterize and exceedingly challenging to estimate. But by assuming that the p covariates are independent within each class, we completely eliminate the need to worry about the association between the p predictors, because we have simply assumed that there is no association between the predictors. So in probability, if you take it, or just, in basic statistics, you learn that two events are independent if the joint probability can be written as the multiplication of each of them separately. So do we really believe the naive Bayes assumption that the p covariates are independent within each class? In most settings, we do not. But even though this modeling assumption is made for convenience, it often leads to pretty decent results, especially in settings where n, which is our sample size, is not large enough relative to the number of features. Because when the sample size is not large compared to the features, then the number of observations we have per features is small, so it becomes even more difficult to capture any dependency between them. So by assuming that they are independent, it makes life significantly easy. So in fact, since estimating a joint distribution requires such a huge amount of data, naive Bayes is a good choice in a wide range of settings. All right. So that's the big idea of a naive Bayes and how to implement it. For that, we need to go into specific examples, and I will show you many examples, both theoretical and in R, how to implement it, and hopefully this will become clear when we do it in practice. So just to summarize, sorry. Generative models for classification. For each class, we have a class-dependent distribution on the features. We use the Bayes theorem to come up with the conditional probability of y given x. That's the whole objective. And if you do the math, this is the key formula or a key expression relationship we have. This is the distribution within each class, and this is the probability that we see any of the responses. Again, we never know these distributions, we only have data, so we have to estimate both f and pi from the data, and estimating f from the data in general is difficult with limited data, so we have to make some assumptions. And we gave 3 examples. One assumption is that it's Gaussian. Different means same covariance. The other one is, again, it's Gaussian. Different means different covariances. And then we have naive Bayes, which doesn't make assumption about the specific form of f, but it makes the assumption that these features within each class, conditional on the class, are independent. And that independence suddenly allows us to estimate this joint distribution from the data. Because otherwise we would need to capture dependencies, and there are so many dependencies, especially when the number of features p becomes larger and larger compared to the sample size.